just 1 minute in French. Donc, juste pour dire que pendant tout l'exposé, je vais avoir une pensée pour Marco. Et donc, je vais improviser pendant 1 heure ou plus sur un sujet qu'il aimait bien, qui est a priori pas lié au feuilletage holomorphe, mais qui en fait l'est profondément. Et donc, je vais faire l'exposé, puis ensuite expliquer la liaison avec les feuilletages holomorphes. So, the title of the talk is Real Hypersurfaces in Cn and Holomorphic Foliation. At first, in dimension 1, I take in C, I see C as R2, and I take a smooth analytic curve at the origin. It's local. And everybody knows that such a curve has a parametrization, and the parametrization is given by an analytic map. It's not, it's good. By an analytic map of this type with complex coefficient on real time. And if you consider the holomorphic map with the same coefficient, you see that this map sends the axis, the real axis, exactly into the curve. So any smooth real analytic curve in C is locally biholomorphic to a line. Okay? It's easy. Now, the same problem, but with 2 curves. And the same problem is very hard. At first, everybody knows standard Schwarz involution. And if you have such a curve, this curve is like a line. For this line, you have the standard involution Z go to Z bar. So here, you have also an anti-holomorphic involution, and I denote by sigma. And now I take 2 curves, 2 transversal analytic curves in C. You see the picture. I have 2 curves, and the angle between the 2 tangents of the curves at the origin is denoted by theta over 2. And I consider the 2 involution map, anti-holomorphic, sigma 1 and sigma 2 as here. And the problem is the following. The problem is the following. It's a problem by Poincaré. The problem says that is it possible to send by holomorphic automorphism, local diffeomorphism, the configuration of the 2 transversal curves into the configuration of the tangent lines. It's easy as problem. Does there exist an holomorphic map which sends the black curve into the black line and the red curve into the red line? An observation, if you consider the 2 linear involution associated to the 2 lines, the composition of these 2 anti-holomorphic map is an holomorphic map, which is linear with a coefficient with derivative exponential of 2ip theta. Okay? And now, if you have an holomorphic conjugacy between the 2 configurations, then you have a conjugacy between the product of the linear involution and the product, the composition of the two non-linear Schwarz involution. And the conjugacy between diffeomorphism, between local diffeomorphism, which says that H1 and H2 are conjugated by the holomorphic local diffeomorphism if you have something like this. It's like the formula in linear algebra. Okay. So if the two configurations of lines are the same up to holomorphic diffeomorphism, then the two compositions of anti-holomorphic involution are the same. So if I denote by H the composition of sigma 1 and sigma 2, if it's possible to send the first picture in the second, then there exists such a phi which conjugates H to its linear part. And Poincaré knows this. And Poincaré has seen that the problem is a difficult problem. And Poincaré says that if the angle theta is not a rational number, then there is a formal conjugacy. Formal conjugacy means that the transformation phi maybe is not convergent. Formal conjugacy. So if it is the case, you have a formal rectification, if you want, of the two lines. And there is a difficult theorem by Siegel and Brujno, which says that if you have Diophantine arithmetic properties of the angle theta, then in fact the transformation phi or H in the transparent is in fact linearizable. What means bad approximation in something like this? You take approximation by a rational number, and you want that there exists a constant such that two constants such that you have something like this. And if you take a generic irrational are of this type. So the classification of a pair of curves is related to problems in dynamical system here on diffeomorphism. When the angle is rational, it's horrible. And the holomorphic classification needs a complicated theory by Ekal and others. And there are many papers on this type of problem. You have paper by Trepro in an asterisk, and you have paper by Ahern and Gong for picture of this type. You take two, for example, two parabola. You have the two involution, anti-holomorphic involution, and you want to give models for this type of picture, and it's a really difficult problem. Now, I consider the dimension 2. When I take a smooth, here I take a smooth real hypersurfaces in Cn, local. And the question is, does there exist a biholomorphism which sends such a hypersurface in a real hyperplane? The answer is no. At first, all the real hyperplanes are the same by the action of linear complex map. So my model is imaginary part of one coordinate. And such an hyperplane, a beautiful structure with inside a foliation by a complex hyperplane. If you take the imaginary part of Zn 0, that is our hyperplane, you have the foliation given by the level set of the real level set by the coordinate Zn, and you have a picture like this. So if you have a real hyperplane, you have inside a complex manifold which are linear of, here you have a dimension 2n minus 1, real dimension. You are in a Cn, and you have hyperplane of type Cn minus 1. So this is im Zn 0. As a consequence, if hypersurface is conjugated to an hyperplane, you have in these hypersurfaces a family of complex submanifolds. I want to speak rapidly about Levy distribution. So I take a real sub-hyperplane, sub-hypersurface in Cn. I take the tangent real hyperplane to sigma, and I take the complex tangent hyperplane, which is, you take the real ordinary tangent space, and you take the multiplication by y, and you intersect with initial hyperplane, and you have a complex. So vector space. So this complex hyperplane is contained in the real tangent space, and it's called the Levy tangent space, or the complex tangent space to sigma. So I give a definition now. The definition says that sigma is Levy flat by definition if the Levy distribution by the complex tangent space is integrable in the sense of Frobenius, in the sense of foliation. So if yes, if you have such a property, then the real manifold sigma is foliated by complex hypersurface. And I give an example you have in the copies. you take, for example, a function, holomorphic non-constant function, which is at any point submersion, and you consider the level set, one level set, and this level set is foliated by the level set f equal t plus yc if c is the initial imaginary part. And there is a beautiful theorem by Elie Cartan, which says that if a real smooth analytic hypersurface in Cn is Lévy-flat, then sigma is locally biholomorphic to a real hyperplane in Cn. And this is an equivalence. And this theorem is local. An exercise, if you take in C2 the sphere S3, which is of codimension 1, then this sphere is not Lévy-flat. There are many different proofs, for example, by maximal modulus principle or by contact form, something like that. By using contact form, in general, an hypersurface is not Lévy-flat. They are very special. Now, I consider real analytic hypersurfaces, but maybe with singularities. For example, a cone, quadratic cone, for example. And I say that this cone or this hypersurface is Lévy-flat if the smooth part of this sigma is Lévy-flat. So, and there is a beautiful theorem by Burns and Gong, recent. And in this theorem, you have the classification, the C linear classification of real quadratic cone, which are Lévy-flat. And I give the pictures, the list of this quadratic Lévy-flat cone. So here I give the equation and the tentative of picture. The first is like in the example where you take a function, here the standard quadratic form of rank k, and you take, for example, the real part equal to 0, and this is foliated by the level set of the same function. And we remark that the foliation by this level set lies, in fact, in the ambient space, in the big space Cn, and not only on the hypersurface. It's an important fact. The second example depends on two variables, in fact. We are in Cn, but the equation is given in terms of two coordinates. In fact, the hypersurface is a union of two distinct hyperplanes with intersection which is real, non-complex. You see in each of the hyperplane, you have a foliation, a red foliation and a green foliation, and these two foliations are not the same. In this case, you have not foliation in the big space such that the restriction to the subspace sigma gives a Levy foliation, if you want. So this case is completely different from this case. The third example is a quadratic, C-quadratic cone. In fact, here we are in Cn, but here also we have two variables, in fact. And the equation of the quadrics is here, Z1 bar minus Z2 bar. And we remark that the action by multiplication by a complex number is compatible with this cone. That means if you have Z1, Z2 in the cone, you multiply by a complex number t, and the new point is in the cone. So that means that if you think in dimension 2, that means that the foliation of the quadric by complex manifold are the lines by the origin, the lines in the cone. And you have another example, which is the more trivial example. It's like in the first or second transparent. Here you have two lines in C, and you take hyperplane, the two hyperplane in Cn, the cylinder, if you want, on these two real lines in C, and here the situation is different because the intersection of the two real hyperplane is a C vector space. It's a Cn minus 1, and the foliation has a vertical Cn minus 1 space, and here you have a global foliation by the vertical lines, which is defined in all the ambient space. And in the same paper by Burns and Gongs, you have something like Morse theorem for Levy-Flack quadratic cone. You take an analytic Levy-Flack hypersurface given by an equation. The quadratic part is exactly the real part of the quadratic form, standard quadratic form of maximal rank, and you have other terms. And the theorem says that this hypersurface is biholomorphic to the quadratic cone standard. It's a beautiful and deep theorem and difficult theorem. And in this case, the foliation of sigma by complex hypersurfaces is like in the case of the quadratic cone, so it's the restriction of an ambient foliation which leaves sigma invariant. Okay. So I give other examples, other constructions which are a little bit obvious, but which give example with very big singularities. You take a map, a holomorphic map, holomorphic function, a germ, and in the target in C you consider a curve, a real analytic curve with singularities. maybe a cusp and a line like you want. And you make the pullback by f of this curve. And this pullback is Lévy flat, and the singularities are a little bit complicated because all the complex hypersurface, the zero of f, is in the singular locus of the sigma, if you want. And the complex foliation by hypersurfaces is given by the level set of the function f. So I want to speak about Clairaut-Brunella example and independent work. The notation are the following: Z and W for the coordinate of C2 with real and imaginary part like this. And you take in C2 the hypersurfaces, the hypersurface given by this equation. In this equation, there is no x. So this is a cylinder in a picture which is in an IR3, if you want. And I cut by the plane y constant, and if you make y constant, you see a parabola T2 equal something in S, linear. So this is a parabola, and there is a special value of y, which is y0, which give a double line. You have a degeneracy of the parabola. And in fact, it's something like Whitney umbrella. Everybody knows Whitney umbrella with, so you have the umbrella and you have a complete line. The line is complete. And there is a fact which says that there is an explicit family of curve, family of parabola, complex parabola, which are contained in M. It's easy to compute. It's a direct computation. And it's easy to see that the union of all these parabola gives all the hypersurface, maybe the smooth part, okay. And as a consequence, this object is Lévy flat. It's Lévy flat, and if you consider the family of curve, family of parabola, in C2, they are the solution of the so-called Clairaut equation. And this is not, this family of curve don't give a foliation. It's a multifoliation. It's a web. The picture is the following. You see? You have a line and you have a family of parabola which are tangent to this line. So at each point, you have two directions. If you want, you have two possibilities of foliation at each point. So if you want to have an expression in terms of differential form, the Clairaut equation gives this differential form with an exponent which is 1/2. So it is a multivaluate one form. But if you make this type of ramification, W equal to T2, then the web becomes a foliation. And I want to show this phenomenon. You see the picture of the parabola here. Okay? And now I take my paper, and now you see a foliation. Okay? And this is the fold, the transformation. So here we have an object which is not a foliation, but after transformation you have foliation. And now I give a theorem by Marco. Theorem by Marco is something like a reduction of singularity for Levi-flat singularities, something like this. In fact, it's a global statement. You have a complex manifold, maybe open, maybe compact. And inside this manifold, you have a real analytic Levi-flat hypersurface with singularities, eventually, with singularities. And the statement, the theorem is a little bit long. At first, there exists a morphism. It's like in a reduction of singularities. You have another manifold, complex C manifold, Y, and a morphism. In the new manifold, you have a new Levi-flat hypersurface, N, and in the manifold Y, there exists an holomorphic foliation, a global holomorphic foliation, which is tangent to N, which give, if you want, the Levy leaves of N by restriction, and with reasonable properties. The first property is that essentially P is an isomorphism on an open subset, and this is an isomorphism on the restriction of this the restriction of the isomorphism to and 0 to the regular part of M is a surjective map, is dominant. And there is a condition which says that restriction of P to the closure of this subset, open subset, to is a proper map. And more or less is the situation of the example of the Whitney umbrella, is something like this. So maybe after transformation, which is not injective map, after transformation, you have an ambient foliation, holomorphic ambient foliation, and this foliation is tangent to the Levi-flat hypersurface, and this is a Marco important theorem. So after this, it seems reasonable to study the pairs of foliation, holomorphic foliation, and hypersurfaces M, which are analytic and Levi-flat, and the Levy leaves are given by the leaves of the foliation F, which are in M. So F, an holomorphic foliation, M, a subspace which is real analytic Lévy flat, and we want to describe this situation. Maybe I want to recall you the first example of linear foliation of maybe Monday, I don't remember, this type of foliation with a vector field, for example. And with lambda, irrational number, negative irrational number. And I've said, recall that the flow is given by t, complex t, x time exponential t, y time exponential lambda t. If you fix a point, for example, this point, then the image, the leaf by this point, that is the image of this map with initial condition x node and y node, then I've said that this is something like real. It's a real dimension 3, real submanifold in situ. In fact, it's explicitly given by an equation which is something like this. Something like this. Okay. Certain constant. This is of dimension 3. And so this object is a Lévy flat in situ with a global foliation linear, and the leaves which are contained in the Lévy flat are dense in this case. Okay? So remember this, because now I say that if you have a germ of foliation and a germ of M which is analytic, then there exists a meromorphic function such that the leaves of the foliation F are the level set of the meromorphic function. In particular, the level set are closed submanifold. And here, the level set are dense. So maybe you have a little problem. But here, it's a global Lévy flat, and the density of leaves is due to the global. That means that if you have a point, you have the leaf, and you go near the infinity, and you return to make the density. But as a local point of view, the leaves are closed, but globally dense. And if the singularities of the Lévy flat M are small in an algebraic sense, then in fact the meromorphic function is holomorphic, and the Lévy flat is given by the real part or the imaginary part of this function equals 0. Like in the case of Burns and Gong. So many Lévy flat are given by the annulation of the real part or imaginary part of a holomorphic function or meromorphic function. So the proof of this result by Linz, Neto, and me is a little bit technical and complicated. And there is a new proof by Marco, which is in print in enseignement mathématique. So, c'est le dernier papier de Marco. OK. On peut faire une pause de 5 minutes maintenant parce que je vais changer de chose. So I want to speak of new example of foliation on Pn and Brunellard conjecture. So at first example. Recall that foliation on Pn and its show theorem are given by a certain form which are homogeneous with integrability condition with Euler condition it's the same condition as for student for homogeneous function, which says that this function is 0. And there is a number which is a degree of the coefficient. And there is an auxiliary condition on singularities, which says that the codimension of the zeros of this form is greater than 2. So for foliation on P2, we are in C3. On P3, we are in C4, and so on. By definition, the degree of the foliation associated to this form omega is nu. So at first, P2. In P2, you have something like Bézout theorem. We know that if you have two curves of degree D1 and D2, then the number of points of intersection of the two curves is the product of the two degree. If you count the multiplicity, here two conic give 4 points. And you have something for foliation. I put here the degree of the foliation. And in general, the number of the singularities it's a consequence of the classical Bézout theorem. The number of singularities is exactly nu2 plus nu plus 1. For example, for degree 0, we have 1 point, one singular point. For 1, you have 3, counted with multiplicity. For 2, you have 7, and so on. As a consequence, we see that every foliation on P2 are singularities. Okay, I give the description of foliation of degree 0. And it's an exercise in P2. There is one foliation, one type of foliation. You take a point, and you take all the lines passing by this point M, and all foliation of degree 0 are of this type. Foliation of degree 0 are radial. So for example, if you want the space of foliation of degree 0 and of P2, it's P2 because it's exactly the data of a point. Foliation of degree 1, generic foliation of degree 1 is given by, in affine chart, is given by the example, the linear example of this type. For this foliation, this lambda is not 0. You have two axes. Recall that you have a point, a singular point, two spatial lines, two spatial leaves, which are the axis. And there is also the axis at infinity. So in this case, you have three lines invariant. So there is three, for the generic case, three algebraic curves, which are, if you want, leaves. In degree 2, maybe a remark. Foliation of degree 1 in P2 are given by a global vector field. So the leaves are the trajectories of linear vector field. They are complete. In degree 2, it's we don't know anything. What we know is that there exist, and you have the example in the notes. There exist examples of quadratic foliation of degree 2, without invariant algebraic curve. In real, when you have a foliation or a vector field in R2 or in P2, real projective plane, you know the so-called Poincaré-Bendixson theorem. Which gives a description of the closure of the trajectories of a vector field in the plane. Of analytic vector field in the plane, if you want, in R2 or in P2 over R. And you know the description. Maybe you have singularities with trajectories which spiral like this. Maybe you have picture like this, compact leaf with singularities. Maybe you have limit cycle. It means you have, for example, something like a circle, and the other trajectories spiral around the circle, and there are some polycycle, which are union of trajectories, and it's possible that you have something like this. Anyway, we know the explicit qualitative description of the closure of leaves, and the problem in complex is what is Poincaré-Bendixson theory. So the problem is the following. It's called the minimal problem. Take a foliation on P2. Of degree greater than 2. And there are singularities. And now you take, the question is the following question. And it's a traduction of Poincaré-Bendixson in the complex case question. Take a regular point and take the leaf passing through this point, and the question is, you consider the closure of these leaves, and the question is, does there exist a singular point in this closure? And we don't know the answer to this problem, and Marco was the investigator of this problem. And if there exists if there exists a leaf L such that the closure of this leaf is disjoint from the singular set, we say that this set is minimal, is a minimal set. And there are properties. If there exist, there are properties. if you take a point in this minimal, if M is in this minimal, then the leaf passing by LM, M is dense. Another M is dense. If M exists, M is unique. If M exists, M cut any algebraic curve. If F has a minimal, has an algebraic invariant curve, then F has no minimal. There are two possibilities. Either M is Levi flat, or M is something like, is a fractal, something like a Julia set, if you know what is a Julia set, is transversally fractal. Because this M is foliated by the leaf of foliation, and if you take a transversal, maybe the picture is like a Julia set, but in the sense of the leaves, there is a regularity which is given by the structure of the leaves. So this is a problem, and Marco had passed many times on this type of question. I give now an estimation of degree of invariant curve, algebraic curve, when there are. And you have in the note recall that in the linear case, which is of degree 1, generically you have 3 lines, and the 3 lines define a curve of degree 3, which is not irreducible. And the foliation are degree 1. I want to give one result. There are 2 results in the notes. I give one because the other needs some notion, and the clock is not good for me. An example of, I take a foliation of degree D on P2 with an invariant algebraic nodal curve. What is a nodal curve? For example, a smooth curve is nodal. In fact, a singular point is nodal if it is locally isomorphic to two axes. For example, take the rational cubic with nodal point. So this is a nodal point. Here I take, for example, a conic and a line which is not tangent, and you have two nodal points. And I take a cusp, and the cusp is not nodal for me. It's not good. So a nodal point is locally like the crossing of two axes. And there are estimations of the degree of invariant nodal curve for f of f. This degree is smaller than the degree of f plus 2. If you go to my web page, there is a preprint which relate this type of problem of estimation of degree with a well-known theorem. You know, if you take a compact manifold, compact Keller, or compact algebraic, if you want, algebraic manifold, and it suffices to have Keller. And if you take a global holomorphic one form, excuse me, complex, global holomorphic one form, then omega is closed. Is a closed form. This is something like Stokes' formula in Griffiths-Harris, for example. There is a generalization of this thing. You take M, compact algebraic, and you take a meromorphic form with pole on D. D is a divisor in M. And you say that omega is logarithmic if omega and the derivative d omega have simple poles along D. And there is a theorem by Pierre Deligne which says following the same. Theorem. If omega is logarithmic and D as normal crossing, like in my definitions. That means that singularities of D are of this type. Maybe you think 2 plane or 3 plane of coordinate and so on. It's a model. They are the model of the singularities. If you have something like this, then the form omega is closed. And I say that the Liouvilian theorem and this estimative for foliation are the same theorem, if you want. Exactly the same, in fact. Now I want to give you some examples in P3 or in P4. P3. And after, I'm a little bit tired. It's necessary to make blow up. Example. In P3. Maybe a remark, or in Pn with big N. In P2, if the space of foliation of certain degree fixed is a Zariski open set in a projective space which depend on the degree. The reason is that in dimension 2, there is no integrability condition. There is no condition. And in P3 and in Pn for big N, it's a little bit more complicated. The space of foliation is something like algebraic, the Zariski open set in algebraic variety of a Z, of a Q, but with many components. Here you have one component, because essentially the closure is a projective space. And one of the challenge for algebraic geometers who works in foliation is to list the possible component. So, at first example, degree 0 in P3. Recall that in P2, foliation of degree 0 of line by a point. And here it's the same. It's a pencil of hyperplane. That is, you give in P3 a line, a P1, a line, and you take all the planes passing by these lines. So the space of foliation of degree 0 is exactly the Grassmannian of the lines. Grassmannian of lines in P3. And this is a space of dimension 4, the compact algebraic manifold of dimension 4. Degree 1 is a little bit more complicated. I give an example of foliation of degree 1 in P3. In P3, I take a P2, a plane P2 in P3. For example, 1 coordinate 0. And you take a point, you take a foliation in this P3. Foliation of dimension 1 in P2, for example, with 3 invariant lines. You have the leaves. And now you take a point which is not in this P2. And now you construct the cone. You construct the cone on the foliation in P2 from M0. So if you have a leaf, complicated leaf here, in P3, you have something like this. Understand? So this type of foliation are called pullback, linear pullback. Of P2 foliation. Now I give you another type of foliation which is not a pullback. I take in C3 which is a chart of P3, I take a quadratic form. For example, this form. And I construct in C3 the foliation by the level set of Q. So the level set are quadrics. So I have a beautiful foliation in C3. And it's possible to complete this foliation in P3 by adding the line, the plane at infinity. So this foliation induces foliation on P3 with leaves quadrics. Now, if you take the following two space, the pullback foliation. And sigma 1 is all this type of foliation. That means all the action of the automorphism, of P3 on the foliation induced by the quadratic form. So you make linear transformation, and you take the closure of this, and the theorem is that the foliation of degree 1 is an algebraic set with two components, and there are these two components. Foliation in P3 with degree 1 is exactly the union of these two algebraic sets. Maybe is due to George Reb. Something like this. And in see in P in degree 2, it's a little bit more complicated. I want to give you an example. I want to say that in degree 2, in P3 or in we have 6 components. We have 6 components. I want to describe one component because it's a beautiful component. Everybody knows twist cubic. In C3, this is a curve. I give a parametrization of this curve. And now I take in C3 maybe C, this curve. I denote by haute C3. It's by definition the group of transformation of affine transformation. C3 goes to C3 affine, irreversible, such that the cubic is invariant by this transformation. It's possible to compute this group, and the fact is this is a Lie group is a complex algebraic Lie group isomorphic to the affine group of transformation of the line. As a consequence, this group acts on C3, and the orbits are surfaces the orbit in C3 of this group Don't be afraid. Don't be afraid.
The group always isomorphic to.
It's the reason is that essentially the reason is that this curve is isomorphic by an automorphism of C3 to a line. It's a reason. And the orbit are surfaces in C3. In fact, the cubic is something like this, you know. And the surfaces are very nice. Transversally, you put a cusp, and you transport this cusp by the group. So you have something like this. If you want, it's more easy to difficult to make the following picture. I take a cylinder of on the cusp. And I make a transformation which send this line to the cubic. So you have something like this. And this curve have big degree 6. And there is a theorem. And these orbits give a foliation of C3s with singularity along the cubic, and this foliation is of degree 2. And the theorem is the following. So I denote this foliation by FC theorem. I take this type of foliation and I consider the group of automorphism of all P3. And this group act on O foliation, and I take the closure. This is sigma, and this is a component of the space of foliation of degree 2 in P3. And the consequence of this theorem is the stability of this foliation. Applies. There exists stable foliation. What is stability of foliation? You say that foliation G in P3, for example, is stable if any foliation which is near G, that means the form which defines the foliation are approximate, are conjugated by a linear automorphism. So I have not said, but this foliation, in fact, can be extended to P3. And the singularities in C3 are exactly the cubic. And in P3, you have all the picture that we have in the triade de Freinet. That means you have the twist cubic, and in the plane at infinity, which is invariant by this foliation extended to P3, you have the tangent of the cubic. The cubic is tangent to the plane at infinity. You have the tangent, and you have the conic, osculatrix conic. So you have all the possibility of a rational curve of small degree in P3, which are line, cubic, conic, twist cubic, which are exactly the singularities of this foliation. It's a nice foliation. Maybe it's, I stop? Okay, yeah. Thank you.